There is this button, you need to push this too, if the screen goes off. So, average momentum is then k over square root of pi integral from minus infinity to plus infinity. dp is the same as dz. I have e to the minus a squared z squared. And instead of p, you write z plus p0. Now the integral involving z itself this is a product of the odd function and the even function over the interval. So this is 0. So what's left is a over p to 1/2 integral from minus infinity to plus infinity dz. The term in p0 remains. If you change the variable from z to y, then this will become, upon substitution, dz will give you dy over a, which will cancel this a. And this integral will give you square root of pi, so this is just p0. So p0 is the average momentum. This being Gaussian, which means it peaked at p0. And then you can probably guess what k is. It's a standard deviation, right? Well, let's compute that. So we define the variance of the momentum, P minus average of P squared, averaged, right? Which is the same as P minus P0 squared. Which is average of P squared minus P0 squared average. So what I need to calculate then is this P squared. So if I calculate P squared, then by definition this is A over square root of pi integral from minus infinity to plus infinity dp p squared e to the minus a squared p minus p0 squared over a. Let's get this. And first we do is replace p minus p0 by z. So p squared in this calculation becomes a over pi to 1/2 integration becomes from minus infinity to plus infinity dz. Instead of p, we will have z plus p0 squared e to the minus a squared z squared. And then we expand this. Well, actually, before I expand it, let me change this to variable y, which is az. So if I do that, then dz will give me dy over a, so I will just have 1 over square root of pi, integral from minus infinity to infinity dy. Instead of z, I have y over a plus p0 squared e to the minus y squared. Then doing this here, this would become y squared over a squared plus 2y over a plus p0 squared. So this becomes 1 over square root of pi. The first integral involves y squared. The second integral will be 0 on the account of the fact that you have y times e to the minus y squared. So this is a product of the odd function and an even function of the integral. And the last term is p0 squared over square root of pi, integral from minus infinity to plus infinity dy e to the minus y squared. But this is square root of pi, so we end up in this case with the result p squared is p0 squared plus 1 over a squared square root of pi integral from minus infinity to plus infinity dy y squared e to the minus y squared. And since our goal is to compute this variance, it's p squared minus p0 squared, so this will cancel this minus p squared. So the variance is just given by this. So if I can compute this integral, which happens to just be a number, we are done. Anyone else how to compute this integral? Backwards? This is a better integral to compute. This is IL. I of alpha, and I will call it specifically I2 of alpha, where I will define I of alpha to be this. I mean, you can do it by parts, right? I'm too lazy. So I know this integral, this one is easy. This one is actually, if I rescale the variable to t, the square root of alpha y, then this integral becomes minus infinity to plus infinity dt 1 over square root of alpha e to the minus t squared, which is square root of pi over alpha, right? So as long as alpha is not 0, we are fine. And so if I compute d alpha, then I get that this integral is equal to integral from minus infinity to infinity dy. When I drop the derivative, when I do the derivative with respect to alpha, I just drop y squared with a minus. So basically, my integral I2 is negative of this derivative. So I know what this integral is, which is minus this here. So this is minus square root of pi, derivative with respect to alpha, of alpha to negative 1/2. Derivative of sum to negative 1/2 power drops out 1/2 power. With this minus sign, I end up with 1/2. I'm still left with this square root of pi, and then I have alpha to minus 3/2, right? Now the integral we need has alpha equal 1. So which is basically I2 at alpha equal 1, right? So if I put alpha equal 1, then I get that this is square root of pi over 2. So variance is 1 over 2a squared of this distribution. And so the standard deviation standard simply 1 over a squared, right? This is nicely convenient 1/2 here, because I have one standard deviation on one side, one standard deviation on the other side. So this interval from here to here is 2 standard deviations. Standard deviation is 1 over a. I apologize. My units were off. That's because variance itself is standard deviation. So basically this coefficient A measures the width of the momentum distribution. So if A is large, this is a broad distribution which looks like this. So A large, momentum distribution like this, looks like this, right? A small, distribution looks like this. And because of our interpretation of what P stands for, which is a momentum, this distribution here, which is wide, doesn't have a well-defined momentum. It's still centered at P0, but it's not very well-defined. This one, on the other hand, has sharp momentum. Point particles should actually have essentially just one value of the momentum. How's my camera doing? Still recording? Okay, don't forget, so we had 4 minutes. Okay. So now we have a full interpretation of what these parameters are. This is the average momentum. This is the width, or the standard deviation of the momentum distribution. Or actually 1 over there, which is the width of the momentum distribution, which means actually that A has the dimension. Oh, 1 over so if I stick in some H bars in there, I could make it essentially behave like a length. This was not a good idea. So, what we need to do next is to compute psi of xt, where if I remember, I had it defined. Now the way we'll do that is basically as follows. We will actually put t equals 0. So this will give us a distribution at t equals 0. And then we'll use the principle of unitary evolution in quantum mechanics, and we will calculate phi of xt as a unitary operator which is applied to psi of xt. I could do it directly over there, but this is kind of more instructive. Do it in this process. So given how much time we have left,